Okay, so for our new unit, we're going to be starting some basic geometry concepts so that we can get into the trig. And what we're looking at is just simple geometric rules. Not going to get terribly far into the basics, like, any 2 points determine a line and all that stuff. But we are going to look at where do the things come from? Where do all our geometric concepts come from? And we defined this a little bit last semester when we did areas and some other things. But we're going to define it a little bit further now. In geometry, everything in geometry originates from the most basic of geometric constructions, which is that right there, which is called a point. It is just a location. It has no dimensions, no length, no width. It is just a location in space. Now, most of what we're going to be doing is on a flat screen, so it's called plane geometry. It's in a plane or on a flat surface. In the real world, things happen in 3 dimensions. So at some points, we'll discuss the difference between that flat surface in 3 dimensions and how it does change a little. Geometry does change a little bit in the 3rd dimension. If I take that point, and we've discussed this part before, and I pull it in a single direction, I create a line segment. Now, for all practical purposes, we're going to call this a line, because a true line goes on forever in both directions, but in real life, we don't have anything that really goes on forever in both directions, except for maybe time, but that's a little abstract. We're not going to worry about that. But anyway, physically, a line segment is what we're going to use as a line. So if you hear the word line, generally we are referring to a line segment. The length of that line segment is equal to the distance that that point was moved. Now, once again, as discussed before when we did areas, I can now take that line segment and I can pull that line segment in a second direction. As long as it stays parallel to its original orientation, the distance I pull it determines a width. Come on now. We're going one of those days. There we go. So this is the length. This is a width. It's that distance we've pulled that line segment. And we've talked about how that defines an area before. Now, going back here, we pulled this point. Remember, said the original point has 0 dimensions. We pull it in a single direction, it now has 1 dimension. Movement in one direction equals 1 dimension. We pulled it in a second direction, it is now 2-dimensional. It has 2 dimensions. So movement in 2 directions becomes 2 dimensions. And of course, the 3rd direction would create a volume that would be 3 dimensions. But what we're more interested in right now is what happens if we go back to that original point and we take it and we pull it in a single direction and we keep going forever. That creates what's called a ray. An array is often used. A ray goes on forever, but a limited ray, where in this case that ray, the arrowhead on the end indicates it keeps going forever. But there's a limited form of array called a vector. You'll notice it looks identical to the ray, but it's not. In a vector, its length is actually important. I could draw the length of that ray however long. I could extend it out here, however long. It means the same thing. It keeps going on forever in that direction. The arrow on the end of this vector does not indicate that it keeps going. It indicates that that's the direction it's going, not the other direction. The length of the vector is its magnitude, is its size. Now, a vector can define, a direction can be defined on a vector. A direction used to be defined using navigational terms. Now, in aviation navigation, they use a little bit different navigational system, but in nautical navigation, east used to be referred to as 0 degrees. Due north was 90 degrees. Due west was 180 degrees. Due south was 270 degrees. And then 360 degrees brought you back to east again. So like this vector here might be at, depending on its angle from due east, that might be 19 degrees. So the direction of that vector might be at 19 degrees. Or the direction of that ray, if it goes on forever, would be at 19 degrees. What do we know about the direction of this ray? Well, it's larger than what? Larger than 90 and smaller than 180. So let's say you're given that this is like 101 degrees. If I combine that vector, or that ray, whichever you want to call it, with this one here, so that one had a direction of 19 degrees. Now what we have is we have two rays, or vectors, or however you want to refer to them, that have a common starting point. If I take that point and I pull it in one direction to create a ray, then I go back to that original point and I pull it in a different direction to create another ray. I've created two rays with a common starting point. That common starting point is called a vertex. And more importantly, I've created an angle. The size of that angle, the original definition of the size of an angle, was the difference in direction. So if this side of that angle is at 101 degrees and this side of the angle is at 19 degrees, the difference is 82 degrees. That's an 82 degree angle. There's 82 degrees between the two sides. Does that make sense? Well, navigation is not used. I mean, once upon a time, over half the population knew how to navigate because it was very important. Now, it's not that important anymore. I mean, those directions basically only come out in land surveying anymore, but the only people that use those, unless you are a pilot. So rather than using that difference in direction to define an angle, we use benchmarks. We know that, of course, a full turn, if you start in one direction and turn all the way around, that is 360 degrees. You start in a single direction, you turn around so you're going the opposite direction, that is 180 degrees. If you make a square corner, that is 90 degrees. Of course, the 180 degrees is half of the 360. The 90 is 1/4 of the 360, or half of the 180. And so our angles now have become defined by what fraction of a complete turn they are. They are like that 82 degrees means that that angle is 82 out of 3/60ths of a full turn. Or 82 3/60ths of a full turn, however you want to word it. So anyway, other notation we can have. This, of course, is a line segment again, or a line. We'll use the word line, but it really is a line segment. If I were going to name it, I would name it like this. That is saying segment AB. If I had the arrows on the end, it would be line AB. But if I just name it like this without that little bar above it, the little line segment above it, what I'm asking is the length. So if I just say AB equals 7, that is telling me that this is 7 units long, whatever units I'm using to measure it in. At some point. So now if we're looking at something like this, what is that name? Well, that symbol up there looks like what? A ray. So it's ray GE. Now for my segment up here, AB, if I had AB or BA, does that make any difference? Absolutely none, does it? Could I have called this ray EG? No. A segment has no starting point. A ray does. A ray has a definite starting point. It starts at G and it goes this direction. A segment doesn't necessarily have that. So a segment, you can switch the points. In array, you do have to have them listed in order from starting point, then into the direction that it's going on forever. Now, if there's another point out here, let's say there's a point M out here, what's the difference between ray GE and ray GM? Absolutely nothing. They name the same ray. When I'm naming a ray, I must name the starting point, but then I can name any point that's along the rest of the ray. It can be the second point that is named for it. Also out of this figure, we could have angle FGE. What would be another name I could have for that angle? EGF. When I'm naming an angle, the vertex must be named in the center. G must be the middle of those three letters. Then I can name any point off of each side. So FGE, EGF would be the same. Also, angle FGM would be the same. It doesn't matter which point I name on the other side. I can name M instead of E. Or angle MGF. Could I name that angle MGE? No, because M and E are on the same side. That's not an angle. I could, however, in some cases, in a case like this, I could name it just angle G because that's the obvious angle there. When I am named, no, we've mentioned this maybe before. There are two angles formed here. There is a minor angle, which is that one, and a major angle, which is that one. You don't need to know those terms. But 99.99% of the time, when we're referring to angle FGE, we are referring to the minor angle, the small angle, because that's usually the angle that we're using for something. Okay, then. Let's take a look at some relationships between these objects. If I have a line, and I construct another line that is going in the exact same direction, just offset a little bit, how do we describe the relationship between those two lines? They're called parallel. Now, the definition that a lot of us have for parallel lines are lines that never intersect. And that is kind of accurate. In 2 dimensions, in a plane like this, that's an adequate definition. Those lines will never intersect. They're parallel because they will never intersect. But in 3 dimensions, let's say I have this line like this and this line like this. Will they ever intersect? No, they won't. Are they parallel? No, they go in way different directions. Parallel lines have to go in exactly the same direction. So a better definition, in 2 dimensions, like I said, never intersecting is adequate. I mean, parallel lines will never intersect. Any lines that do intersect cannot be parallel. There is no such thing as lines that don't intersect that are not parallel in a plane or on a flat surface. But as we saw in 3 dimensions, we can have lines that don't intersect that are definitely not parallel. So a better definition of parallel is, the technical jargon is everywhere equidistant, or always the same distance apart. Okay, so these lines are parallel. Distance, by the way, is always measured perpendicular. So to measure the distance between them, I have to measure perpendicular from this one to the other one. Well, since they're parallel, of course, it's going to be perpendicular to both. What's that? Well, there's a debate on that. If parallel arches, by the technical definition, they can be, because they can always be the same distance apart. But there's a debate on whether that's parallel or whether it's concentric. Because I would say that the more proper term would be concentric. They have the same center. But I don't know, that could be debated, I suppose. I wouldn't mark it wrong if you called them parallel. So anyway, with our parallel lines here, let's take another line and cut across them like this. That line that cuts across them is called a transversal. Transversal actually cuts across any two lines, but it's more interesting when it cuts across parallel lines. When I have two parallel lines, I have a set of parallel lines cut by a transversal. If I look at one of the angles, let's look at this angle here, and let's say that that is 78 degrees. If I want to analyze the rest of the angles here, I can consider the relationship. If I take this line here and I slide it back up here, you'll notice it sets right on top of the other line, which it should. They're parallel. So what does that mean for the relationship between this angle and this one down here? They have to be the same. So this one here must also be 78 degrees. Now there are some relationships between angles that we need to know. If we have two angles that add up to a straight line, let's say we've got this angle here is 109 degrees. Do we know what this angle has to be? Yeah, what's it got to be? 71. How do we get that? 180 minus 109. So this up here, this angle would have to be what? 102. 180 minus 78. Well, what does this angle have to be? Well, it has to be 78 because these two have to add up to 180. These two angles here are what we call vertical angles. They are formed by two intersecting lines on the opposite sides. They're formed by the same rotation. This rotation here and here must be the same. Those two angles must be the same. So, of course, that means then that this one over here must be what? 102. Well, this one's 78, so this one is 102. This one is 102, and this one is 78. Now, if this were a formal geometry class, we'd be looking at all sorts of crap. Alternate interior angles are the same. Alternate exterior angles are equal. Corresponding interior angles are equal. Or corresponding interior angles, as you say, are supplementary. That would be these two. They add up to 180. What we're going to do is we're going to define Hof's rule. Hof's rule states, at least as of right now it states, when parallel lines are crossed by a transversal, all angles formed are either equal or supplementary. Supplementary means they add up to 180 degrees. Supplementary. Now, of course, along with supplementary, we could have two angles that add up to 90 degrees. Let's say this angle here is 28 degrees. What's this one here have to be? 62. Adds up to a right angle. This is supplementary. Hof's rule. When you have two parallel lines that are cut by a transversal, all angles formed are either equal or supplementary. So here they add up to 90 degrees. That is complementary. Now, if you're anything like me, you remember those words and you know that one is 180 and one is 90, but it's hard to remember which one. Well, 90 degrees is a right angle, correct? And in here, I will compliment you when you are right. That's how I always remember it. You get compliments when you're right. So complementary angles add up to a right angle, add up to 90 degrees. So then we can have, we've had lines that are parallel. We can have lines then that intersect in a special way. These lines intersect in a right angle. Now, of course, if that's 90 degrees, what's this angle have to be here? 90 degrees, because they have to add up to 180. What's this angle have to be here? 90, because those two have to add up to 180. Of course, this one then is 90. All the angles are 90. Two lines that intersect at a right angle are called perpendicular, because all angles formed are 90 degrees. Now, perpendicular can actually be a much more powerful term than that in 3 dimensions. Perpendicular, if a line is perpendicular to a plane, that means it forms a right angle in every possible direction that you can measure it. So it forms a right angle in every direction. So it'd be coming straight out of the board. Whether you measured the angle on top, that's 90 degrees. On the side, that's 90 degrees. On the bottom, that's 90 degrees. No matter where you measure the angle, it's 90 degrees. That's what perpendicular means. So we can have 2 lines that are parallel. They never intersect, and they're always the same distance apart. We can have 2 lines that are perpendicular. And then we can have 2 lines that intersect like this, but not in a right angle. They intersect, but not perpendicular, which is called oblique. What's that? You're talking about opaque. Nice try, though. Close enough. So anyway, let's keep going with this. We've measured our angles. We've got all these relationships. We've got supplementary. We've got complementary. We've got transversals on parallel lines. We've got parallel lines. We've got perpendicular, oblique. Let's actually now start focusing in on the angles themselves and what we're going to be doing with them. So we've talked a little bit already about angles being measured in degrees. You know, this is less than a quarter turn, so we know it has to be less than 90 degrees. Let's just say that were, I don't know, 81 degrees. How would we determine how big it is? Well, if you don't have it on a computer screen, it's on paper. What you'd use is a protractor. Do you guys still get a protractor in your drafting kit? No, you don't? Okay, you'll need to pick one up sometime in the next few days. That'll be one of your assignments for over the weekend, is to pick up a protractor. You can get them for like $1 or $2. I think their bookstore has them for $2 or $3 if you need them. But go to Walmart or something, you get them for like $1. A protractor just looks like a half circle. Most of them are open in the center just to make them a little lighter and cheaper, like that. And the protractor usually has a 0 point right here, and a 0 line across the bottom. And then the angles are measured across it. Now I'm going to draw out a little bit larger version here. What I usually do to measure an angle, you put your 0 point on the vertex, like that. Oops. Pretend that looks like half a circle. And you put one side of the angle along that 0 line across the bottom, like that. Pretend that's straight. So this would be 0 degrees. Now this is labeled, of course, 90 degrees on top, over here. Wow. Pretend those lines are evenly spaced. Now let's say this spot right here, if I'm looking at this line, which we're just slightly past, if we look at it, it might have 2 labels. It might have 120 degrees and 60 degrees on it. Which one of those do we use? Well, for this one, which one would we use? We'd use the 60. How do we know it's the 60? Now, some of you have been told, well, you go here, this is at 0, so whichever scale is at 0, that's the one you use. And it's not the 180 side, it's got to be the 0 side because that's where the initial side is. But we don't need to worry about that. How do we know it's 60? It's a smaller angle. It's an acute angle. Acute angles are less than 90 degrees. So we use the number that's less than 90 degrees. If it were starting over here and going like that, well, then it's an obtuse angle. So an obtuse angle, then we'd use the one bigger than 90 degrees, because an obtuse angle is always larger than 90 degrees. So you don't need to necessarily follow the scales. Just you should be able to tell really quickly which of the two numbers you're going to use. Well, for our purposes, there are times when measuring to the nearest degree is not precise enough. Just like measuring to the nearest foot is not precise enough and need to go down to inches, we need to go down to parts of a degree. So that symbol equals 1 degree, of course, which is 1/360th of a circle. Smaller than 1 degree, just like 1 foot contains 12 inches, 1 degree contains 60 minutes. The symbol for minute is a single quote, just like the foot symbol. 1 minute contains 60 seconds. The symbol for seconds, by the way, is the double quote. 1 second looks like that, just like an inch symbol. So when you're dealing with degrees, you have to be very careful not to confuse it with feet and inches. Usually when you're dealing with degrees, you have a degree there. So you might have, like 17 degrees, 32 minutes, 30 seconds. So because you have degrees in front of them, it's obvious that that's not feet and inches. But be careful. And very seldom will you deal with an angle that's less than 1 degree, so you'll just have the minutes and seconds. I can't think of any application in woods where you would need something that small. And I'm going to put this right up front for you guys in woods. Measuring down to anything less than like 1/4 of a degree will never happen. Why are we presenting this to you? Well, because the machine tool students take a similar math class to this. In fact, your math class, if you decided to switch over to machining, to CNC or machine tool, would cover their requirement. So I have to show you it's very important for them to have degrees, minutes, and seconds in their angles, because they're dealing with metals which are much more precise. So we have to include it just in case. Realistically, in woods, dealing with woods, less than 1/2 or 1/4 of a degree is never going to, even down to 1/4 of a degree is a stretch. 1/2 a degree is about the worst you can get. The only place I can see anything being more precise than that is if you got into countertops. If you get into countertops, cutting the miter in a countertop, you may have to get down to less than that, especially if you're dealing with solid state like granite or marble or anything like that. Then you would have to get into more precise measurement. Those are usually laser measured and laser cut. There's a cut with machines, but I mean, if in your field, in the construction field, you could end up in that area where you would need to be able to go to that. But I mean, even in cabinetry, anything less than 1/4 of a degree is almost unmeasurable with wood. That you can't really account for that in wood. But anyway, let's say I have an angle that is 19.64 degrees. This is what we call decimal degree notation. From here on out to be known as DD, decimal degrees. I can convert that into degrees, minutes, and seconds. How do I do that? Well, the 19 is going to be degrees, so I'll take the 0.64 times 60 to convert them into minutes. That is 38 minutes. Then I'm going to take the 38 off of there to leave me with 0.4 minutes, and I'm going to change that into seconds. Times 60 will give me 24 seconds. This is what we refer to as degree, minute, second notation. From here on out to be known as DMS. So DD and DMS are terms that are going to be very, very important to us. So now let's work on this conversion a little bit. let's say I have 47 degrees. Well, let's do this. 47.914 degrees. And I want to convert it to degrees, minutes, and seconds. What will my first step be? Just take the 47 degrees. You're correct. So take the 0.914 times 60 to make it into minutes. I get 54.84, so what do I do with that? 54 minutes. Take away the 54, yeah, and then times 60 to give me 50.4 seconds. In your seconds, it is okay to have up to 1 decimal place. Realistically, if you rounded that to 50, I wouldn't care. I'd be okay with that. In woods, you're never going to measure down to a second, much less a tenth of a second. The most precise measuring I've ever seen in this area actually is Hutchinson Technologies. They do measure down to the nearest 5 minutes. 5 minutes. Now, that's not even a second. That's not even down to the nearest minute. So, I mean, they do measure some. There's some of their stuff that they have worked with that they actually measured down to the nearest millionth of an inch. Yes. That's getting tight. You're right. That is not a lot of room for error. We can still have up to 1 decimal place in our seconds, yes. But like I said, if you rounded that off just to 50 seconds, I'd be okay with that.
What's the world's roundest object?
Roundest object?
Yeah, there's a silver ball or whatever.
Yeah, I couldn't even tell you.
That's gotta be like silver.
Actually, that's not measured by degrees. That's measured usually by radius. So anyway, let's take out, I'm going to have you guys try one. 31.664 degrees. Change it into DMS for me. I'll give you a minute to do that. Okay, what'd you come up with? $50.4. You do 50 seconds would be fine.
No, why the minutes?
You can't round minutes. Nope, you never round the minutes. Minutes, you just take what's before the decimal and you use it. What's after the decimal becomes your seconds. After you multiply, of course. So here we would have done 31.664. Of course, the 31 comes off as the degree, so we subtract 31. 0.664 times 60 gives us the 39.84, so 39 minutes, so we subtract off the 39. Then the 0.84 is times 60 to give us our seconds, which is 50.4. If you'd rounded it to 50, that would be okay. So how about the other direction? What if I give you 29 degrees, 13 minutes, and 45 seconds? And I want you to convert it back into decimal degrees. Well, our first step is going to be with the 40 seconds. We're going to divide that by 60 to get 0.75 minutes. What are we going to do with that? We're going to add the 13 to it. So it's now 13.75 minutes. Of course, we're still at 29 degrees. What are we going to do with that? Divide by 60 to turn it into degrees. So 13.75. Oops, helps if I get the 3 in there. 13.75 divided by 60 is 0.2291666. What am I going to do with that now? Add my 29 degrees. 29.2292. Unless it is otherwise stated, where to round off your decimal degrees, put decimal degrees to 4 decimal places, unless you're told otherwise. On all my quizzes and tests, go to 4 decimal places, unless you're told otherwise. Let's have you guys try one. 43 degrees, 42 minutes and 18 seconds. Convert that into degrees, minutes, and seconds for me. Convert it to decimal degrees, actually. Sorry. What'd you come up with? 43.715. Let's take a look. So it's 18 divided by 60 is going to give us 0.3. Then we're going to add 705. So we're going to add the 42 to it. So 42.3. We're going to divide by 60 again to convert that into degrees. So 0.705 plus the 43 degrees. So 43.705 decimal degrees. How you guys feeling about these so far? Really good? Well, let's go one more step.
We do one more of those for next
Like this?
Yeah.
Okay, sure, we can do one more. 34 degrees, 24 minutes, 48 seconds. Convert that into decimal degrees. You get 34.4125? Yeah, that's right. 41333. You're right. That's what I get for doing it in my head. So we've got 48 divided by 60. Then we're going to add the 24 to that. Then we're going to divide that by 60 and add the 34 degrees. So 34.4133333333. Okay, now just like adding any other measurement, any other number, we start from the right, work our way back to the left. We're going to add the seconds. 19 and 32 make 51. Do we have to carry anything? No, where would we have to carry? If we went over 60. 32 plus 14 is 46 minutes. And then 41 plus 12, 53 degrees. 52 degrees, 46 minutes, 51 seconds. Doesn't matter. No, doesn't matter. So for adding here, 27 and 52 makes 79. Of course, that is going to be carry 1 minute, which is 60, leaving us with 19. Now 1 and 43 is 44, plus 31 is 75. We're going to carry the 1 degree, and we're going to leave how many minutes? Well, minus 60 is going to be 15 minutes. Does everybody see where we're getting the 15 and the 19? We're subtracting 60 from what we got for our total. Because that's 1 degree. We take 60 of those, that gives us 1 degree. This one here? We took 60 out of the 79 to get 1 minute. Yeah, we split the 79 into 1 minute and 19 seconds. We kept the 19 seconds, carried the 1 minute. So this is now 29 and 1 is 30, plus 18 is 48 degrees. 48 degrees, 15 minutes, 19 seconds. We're going to have 52 degrees, 17 minutes, 38 seconds, minus 37 degrees, 52 minutes, 41 seconds. Subtracting, of course, is where we end up having to borrow. So 38 minus 41 cannot be done. So the 17 is going to become 16 minutes. What's this become? 98. Where did 98 come from? We borrowed 1, which is 60 seconds. Plus the 38 is 98. No. That would confuse you a little bit. Trust me. So now 98 minus 41 is 57. I mean, if that works for you, go ahead and do it. But that confuses a lot of people if you do it that way. So now 16 minus 52 won't work, so we're going to borrow from the 52. That's 51. And this is going to be now 76. 76 minus 52 is 24. 51 minus 37 is 14 degrees. Any questions on those? Adding and subtracting is pretty much just like adding and subtracting any other measurement. You look confused, Mike.
No, I'm not.
Other Mike. You good? Okay. Sorry, you're used to me calling it. 23 degrees, 52 minutes, and 19 seconds. Times 4. Well, 19 times 4 is 76. Of course, that's bigger than a minute. So we're going to carry the 1 minute. What's going to be left? 16 seconds. 4 times 52 is 208, plus 1 is 209. We can take 3 degrees out of that. 3 times 60 would be 180, which leaves us with 29. Everybody see where we got the 3 and the 29? Questions? Yeah. We take 60 out of 209 3 times. That was 180. So it's like a division and remainder again. 209 divided by 60 is 3, with a remainder of 29 left over. So now we've got 4 times 23 is 92, plus 3 is 95 degrees.
So why do you use
Because you multiply before you add. Always multiply before you add. Order of operations. So let's say I have 19 degrees, 47 minutes, 18 seconds. I'm going to divide it into 6 equal pieces. Just like doing our division with our other operations, other measurements. 6 goes into 19 3 times. That'll be 3 degrees. 3 degrees times 6 is 18 degrees. Subtracting gives me 1 degree. Before I can bring down the 47, I convert my 1 degree into 60 minutes. And now I bring my 47 is 107 minutes. Divided by 6 is, what is that, 17? 17 times 6 is 102. Leaves me with 5 minutes left. Before I can bring down my 18 seconds, I have to convert the 5 minutes into 300 seconds. 5 times 60. So now that's 318 seconds. Divided by 6 is going to be 53. What do you think? Good stuff? Anybody feel a hemorrhage coming on yet? Well, that's good enough for our first hour of class. Page 461 in your book, it is exercise 20-4. There is 1 through 36 the odds. On page 464 in your book, exercise 20-5A, 1 through, I should say 1 through 35 the odds, I guess. 1 through 35 the odds. And on page 467 through 468, exercise 20-5B, 1 through 33 the odds. As always, do some of the easy ones, skip ahead to the more difficult ones if they're going well, but there's enough there to practice if you're struggling. It is also break time. I actually went 1 minute past break, so if you want to take a break, we'll start up again at 1:31.